When we think of space, we often imagine a vast emptiness scattered with stars, galaxies, and glowing nebulae. But the truth is far stranger. Between the threads of the cosmic web, those long filaments of galaxies and dark matter, lie enormous regions of almost nothing. They are called cosmic voids, and they are the emptiest places in the known universe. No stars, no galaxies, just an ocean of darkness stretching across hundreds of millions of light years. But here's the question. If these regions are so empty, why do they matter? And what could be lurking in the vast silence? Let's journey into the void. What are cosmic voids? Cosmic voids are the giant underdense regions between the large-scale structures of the universe. While they're not completely empty, they have far fewer galaxies, stars, and matter than average. Imagine the universe as a sponge. The web, or foam, is where galaxies cluster. The bubbles in between, that's the void. Voids are immense. The average void spans about 30 to 300 million light-years across. The largest ever found, the Boötes Void, is nearly 330 million light-years wide and contains very few galaxies within its volume. That's more than 250,000 Milky Ways wide and almost completely dark. But why are they there? How voids formed? In the early universe, matter wasn't spread evenly. Quantum fluctuations seeded regions of slightly higher and lower density. Over billions of years, gravity amplified the denser regions, pulling matter inward to form stars, galaxies, and clusters. The underdense areas? They were left behind, expanding faster than average, growing into vast voids as the rest of the universe condensed into structure. In a way, the voids are the cosmic leftovers, the forgotten spaces between the visible. But make no mistake, these voids aren't irrelevant. They could be the key to understanding the universe itself. Why voids matter? Cosmic voids are sensitive probes of dark energy, the mysterious force driving the acceleration of the universe's expansion. Because voids expand faster than denser regions, they exaggerate the effects of dark energy. By studying their size, growth rate, and shape, scientists can better constrain models of cosmic acceleration. Voids also help test general relativity and alternate theories of gravity. In low-density environments, modified gravity theories predict different behaviors than Einstein's equations, making voids perfect testing grounds. And then there's the mystery of what we're not seeing. The cold spot. Mystery. In 2000, data from the Wilkinson Microwave Anisotropy Probe, WMAP, revealed an unusually large and cold region in the cosmic microwave background, the oldest light in the universe. This region, dubbed the CMB Cold Spot, was cooler than expected and too large to be explained by standard models. Later observations by the Planck satellite confirmed the anomaly. One explanation? A supervoid, a colossal underdensity stretching over 1.8 billion light-years, may lie in that direction, draining energy from photons as they pass through. But the numbers still don't add up completely. Some physicists speculate the cold spot could be a hint of something deeper, perhaps a collision with another universe, or a topological defect from the early universe. Either way, voids are becoming a focal point in the search for cosmic anomalies. Could anything exist in a void? Surprisingly, yes. Voids aren't completely empty. They contain gas, dark matter, and isolated galaxies, sometimes called void galaxies. These galaxies are often smaller, less evolved, and form in isolation, unshaped by interactions or mergers common in denser environments. Studying them gives scientists a glimpse into how galaxies evolve without external interference, like observing cosmic evolution in a lab. Voids may also be home to faint dark galaxies, composed mostly of dark matter with little or no visible stars. Some theories even suggest voids could contain exotic physics, topological defects, remnants of symmetry, breaking in the early universe, or even cosmic strings hiding in plain sight. A gateway to the unknown? Here's where science blurs with speculation. Because voids are so large and mysterious, some theorists wonder, could they be gateways? One hypothesis is that voids represent more than just absence. They could be interfaces between different quantum vacuums, or even regions where the fabric of space-time is thinner. In some inflationary models, voids may be where the energy of the universe was lowest, possibly hinting at different physical constants, alternate realities, or weak spots in the cosmic field. Others suggest voids could act like cosmic insulation, expanding to isolate regions of the universe from one another. Could we travel through one? Could something else come from one? We don't know. But the questions are getting louder. What's next in void research? Upcoming missions like Euclid, the Nancy Grace Roman Telescope, and the Vera C. Rubin Observatory will map cosmic structures in greater detail than ever. They'll reveal the shapes, sizes, and motions of voids, testing the influence of dark energy and gravitational laws across vast distances. Simulations like Illustris and Millennium are modeling the evolution of voids and how they interact with galaxies and dark matter. The goal? To use emptiness as a tool, to learn what we can't from matter alone. Because sometimes the best way to understand the universe is to study what's not there. Final thought. Cosmic voids are nature's quietest regions, silent, dark, and seemingly lifeless. But in that stillness lies potential, clues to the origin of the universe, tests for our deepest theories, and possibly a path to answers we haven't even thought to ask. Here on Infinity Beyond, we believe even the void has a story to tell, and we're here to listen.